let's get started with this course. This is perhaps the most abstract course in the whole curriculum, but I think one of the most fundamental courses for any computer scientist to know. Now, the really interesting stuff in this course is not going to help you write a program per se, and it's not going to help you build a computer per se. But it'll help you understand a lot more about what people have thought about in the last 50 years about computer science as a science. And it's about what kind of things can we really compute mechanically, how fast can we do it, and how much space does it take us to do it, how much memory does it take us to do it. And because of that, the course is called Theory of Computation. So like lots of abstract courses and courses that have a lot of really cool thinking and neat stuff in it, especially in computer science, there are lots and lots of applications that come out of this course. Things that are pretty much serendipitous. All of compiler design and theory about building compilers and writing programs to translate languages comes from theory of computation. And not a direct application either, but more a kind of a side effect. It turns out that some of the models of computation that we discuss happen to correspond to programs that help us write compilers. And there's lots of other applications as well. When you talked about computer architecture, you modeled a particular processor with a finite state machine. The idea of a finite state machine originally comes from theory of computation. When you do any string searching in any word processor or any kind of editor, that uses a finite state machine. When you do any kind of compiling or representation of a language like XML, you describe it with a grammar. And that grammar is the next level of model of computation. So what this course talks about is different models of computation, different kinds of things you can use to compute stuff. Now, what does it mean to compute something? In this class, it's going to be something very, very simple, because we want to abstract it all away from all the specifics of the machine and all the specifics of problems you see. So we abstract it away in this style. We imagine that all we're doing is dealing with programs or computations that take an input. Somebody sends it an input, and the program sits and stares and thinks and calculates and computes, and then says yes or no. Do I accept this input or I do not accept this input? No actual number crunching or anything like that. Whatever number crunching involved is all in order to decide yes or no. So in order to do that, we simply think of things we want to compute as a set of things. And normally the things are very simple. We pick an alphabet. It can be as simple as a binary alphabet. And it could even be a unary alphabet, just one symbol. And we consider strings along that alphabet. So what's an example of something you might want to compute? Say, the set of binary strings. That means strings over the alphabet 0, 1 that end in 0. Not a very hard thing to compute. Somebody gives you a binary string. If you're a human being, you just look at the end of it. You see if there's a 0. If there is, you say yes. If there's not, you say no. You could all write a computer program to do this, certainly. You could have probably done it, some of you, before you came here. It's a very easy program. You look at the end, you see if there's a 0. There are other things that are harder. What if you took a piece of Java code and turned it into a binary file and wanted to know whether that really came from a legitimate piece of Java code or whether it's just some junky binary file that represents something else? Does this binary file represent a legitimate Java program or not? So we can write the set of binary strings that represent legal Java programs. So can you do that? Can you write a program that does that? I don't mean you personally. Could somebody write a program that does that? They better be able to. Otherwise, when you write your Java program and you say run this, what checks that it's a legitimate? What's giving you all those error messages, right? It's not some little mouse sitting in the machine saying, that's not right. Error on line 32. Or there's a program that looks at this and that does it. And it does more than just say yes or no. It actually spits out output. That's what compiler design is all about. So that you can still do, but it's a lot harder computation than that. And let's go one step further. The set of binary strings that represent legal Java programs that never infinite loop. That's probably not English, but you know what I mean. Loop is a verb there. That never go in an infinite loop no matter what input you would give them. Is there a program that will look at your Java code and tell you that, yes or no? And the answer is there isn't any such program. It's impossible. There's no way to compute this. No matter how hard you try, it's not going to work. It's going to either give you the wrong answer or it's going to run forever and never give you any answer. Your program that you try to write to do this doesn't exist. So that's what we're talking about in this class. What can you compute and what can't you compute? And what kind of models do we have to do this computation? Your own sense of how you do computation now is a programming language. You know Scheme, you know Java. That's one thing. But we're going to abstract all those details away and get down to the root of what a programming language really is. And maybe the most popular way to view a programming language with everything stripped away is called a Turing machine, invented by Alan Turing. And it's a very simple machine. We won't talk about it yet today. We're going to build up to a Turing machine. But Alan Turing in the might have been the 1940s when he invented this. He died in the 1950s. Invented an abstraction, a mathematical abstraction that he thought was a complete representation of how we might do computation. To the extent that anything that you do on a normal computer with a normal programming language could be done on his machine. You could write a program for his machine that does the same thing. And his machine's very, very abstract and simple, but because of that, we can prove really interesting things about it, like the fact that this can't be computed. So what we're going to do in this class is work our way up from a much lower level. One thing when you define something abstractly is, here's a nice Turing machine. It's got arms, it's got legs, it's got a brain. What if I cut off its left arm? Can it still do everything it could do before but just take a little longer? Or is it actually handicapped and it can't do certain things that it used to be able to do? For example, the set of binary strings that represent legal Java programs. I know that I can write a program to accept those. Therefore, I'm sure I could write a program for a Turing machine that would accept those. But what if I cut off the Turing machine's left arm, metaphorically? Is it possible that I can't do this anymore? And I'm cut back actual power. Or maybe it just takes me longer to do it. Those are the kind of questions people ask in this class, in this course. That's the kind of questions scientists wonder. How much can I chop off of a Turing machine and still be able to do it? And then we're going to abstract it out. We're going to start with the lowest level, which is a finite state machine. And we're going to work our way up, building pieces on it until we get up to a Turing machine. And then start exploring the twilight zone, which are problems out here which can't even be computed by a Turing machine. Right, so that's the big picture. Are there questions about that so far? Little bullseye. One more. The simplest kind of machine we're going to consider is one that doesn't have as much power as programming languages. One that's simpler, called finite state machines. I'll abbreviate it, FSM, finite state machines. And you've seen these before, and you've seen their applications before. That's the smallest, simplest level. They can compute certain kinds of sets. They can decide certain kind of things, like whether there's a 0 on the end of a string. But they can't do things more complicated, like figure out whether something's a legal Java program. There's a lot of other things they can't do also. There's a lot of interesting things they can do. Outside of this, if you add on some power to the machine, is a class of sets that can be recognized by a more powerful machine. And those sets are called context-free languages. A set of strings is often called a language, not at all to be confused with a programming language. A language is nothing more or less than a set of strings. So the set of strings that have zeros at the end of them, that's a language, and you can recognize it with a finite state machine. Context-free languages are languages that are more complicated than the ones that can be accepted by finite state machines, and they also include the finite state machines also. So they're a larger group. All the stuff about compilers, legal Java programs, all those sets of strings, those languages, they're inside here. So legal Java programs are in here.
Context-free language?
In context-free languages. Then we bump up another level to Turing machines. That's full-level computation. That means anything that can really be computed with a computer, with any normal programming language, can be computed by these machines. So this includes everything that you know how to do. And way out here in the twilight zone are problems that we call undecidable. There's no program anywhere mechanically that can figure out the answer to these questions in general. No algorithms to figure out the answers. This is a blueprint for the course. Now I should say, as we get into more detail, this blueprint will become more refined. There are subcircles. There are sometimes overlapping circles. There are all sorts of other relationships between these levels. Inside the Turing machine level itself, there are hierarchies. P and NP are both inside the Turing machine level. Okay, if I made another subcircle, P would be on the inside, NP would be on the outside. There's a whole hierarchy of complexity theory that takes place here. All the applications to compiler design take place here. And all the applications with finite state machines take place here. But it's this hierarchy that will give you a blueprint for the class.
These are all machines except the outer layer?
Yes, they all represent machines with different amounts of power. And well, you'll see that there's different ways of actually describing languages. One way is by a machine. Another way is by a grammar. And a third way, and it works only on some levels, is by something called expressions. So there's different ways of describing these classes of sets of strings or languages, but you can think of it for sure as just more powerful machines going up the line. This level in particular is going to be split into two. It turns out that the two levels that this splits into end up not giving any extra power in these levels. In other words, there's an extra booster arm that you can throw into finite state machines, but it turns out not to give it any extra power. You know, it's like if somebody runs a marathon in 4 hours and you give them lots of extra carbohydrates before, so they'll run the marathon in 3:50, but it's not going to make them a really better marathon runner. So they stay the same, they're just a little faster. But in this level, if you throw in a little bit of extra power, you actually end up gaining new languages that you couldn't do before, and it splits this set into two. Back in this level, when you throw in that extra bit, things stay the same again. So this level will get partitioned later on. Whee! All right. So it's time to get down to some more specifics. Okay, let's start down here. You've all seen finite state machines before. I'm going to pretend you never have. And I'm going to teach them like I always teach them. You're going to read the book. The book has tons of formalism, even though it's a very nice, intuitive book. There's lots of ideas behind the proofs. Nevertheless, to write a real book for this stuff, you have to be very careful. Make sure you don't say anything vague. That's exactly the opposite of what's going to happen in class. I can say all the vague things I want because I want to give you the idea of what's really going on. And if you want to find out the real nitty-gritty detail, and if I say something that's 100% completely rigorous, it's right there for you to check. And just ask me a question, too, because I know all the rigor behind it. But it's just really bad to teach this course by going toward rigor. Some of you might have remembered some of the speakers we had during this year, one of whom particularly talked about this stuff and did exactly that. And it seems much more difficult than it really needs to be. So I'm going to explain what a finite state machine is by showing you an example and then pointing out in the example what the real traits are. So let's start with an example. Let's start with strings that have an even number of zeros, binary strings that have an even number of zeros. I should mention, our sets of strings that we're talking about, they don't have to be over the alphabet 0, 1. Right? I mean, Java programs are over an alphabet of A to Z, and 0 dot dash up to 9, and commas and semicolons and various other things, parentheses, close parentheses. So this alphabet can be very large. But for the purposes of understanding the abstractions and what's really going on in this class, we hardly ever need to consider alphabets that are more than 2 symbols. 2 symbols kind of gives you this exponential help over 1 symbol. And after that, it's just convenience. So we'll always assume that it's binary strings unless I say otherwise. So we want to consider the set of strings that have an even number of zeros, a set of binary strings with an even number of zeros. And we're going to describe these things called finite state machines by actually doing it for this problem. So here's what a finite state machine looks like. It has states. The states represent some kind of memory about the problem that you're dealing with. If you want an intuition for what can be done with a finite state machine, it's anything you can do and solve by remembering a finite amount of information. If you use that gut instinct rule, you'll be able to almost triage any set and say yes or no, it can be done with a finite state machine or not. If you ask yourself, can I write a program for this using a finite amount of memory? Could I figure out how to do this storing a finite amount of information? So in this case, I want to give you a sense of how to do the design of finite state machines. This is going to be an easy one, but there's plenty of hard ones. You really want to get a semantic meaning to each state. So this state will be things with an even number of zeros. And I have another state that will be an odd number of zeros. And we're going to start here, meaning that before we've seen any symbols of the string that we're considering, we now have an even number of zeros, namely 0 zeros. We haven't seen anything yet. And now the machine is going to, imagine the machine looks like this. It's over here, and then there's a little tape here that has a particular string on it. 0, 1, 0, 1, 1, 1. So this should be accepted. It should say yes. The machine is going to have a little head, little arrow, a little head that looks at the symbol and moves strictly left to right across this tape. And as it moves from state to state. That's all it does. That's the simplest kind of computation you could possibly have. Remember, a finite amount of things. Read your candidate string left to right and move back and forth. So let's put in what's called the transition function, the thing that tells us where to go as we see symbols. If we're in this state, we have an even number of zeros, and we see a 0, then we're going to switch over to that state. And what else might we see? We might see a 1 instead of a 0. What would we do then? Stay here. And that takes care of this state. In fact, every finite state machine should have exactly one arrow coming out of each state for each of the symbols in your alphabet. So in binary strings, you got 2 arrows coming out. And now you move on to the next state. And in fact, if you structure your design of finite state machines in this way, actually writing the states down first without any arrows, modeling the problem semantically by giving information in the states, and then only later filling in the arrows, you'll have a much, much easier time doing it. And if you have trouble deciding what information needs to go in the states, that's where you should stop and think, and not after first putting in some arrows, because that will just get you perhaps on the wrong track. All right, so who can fill the rest of this in for me? Smiley Donna?
You get a 1, come back to yourself.
Done.
You get a 0, go back to yourself.
Good. All right, this is 80% of a finite state machine. This arrow indicates that I start here in this state. There's one state that is uniquely given as the start state. That tells me where I begin. These arrows tell me where I go based on different symbols. And there's one more piece of information, and that is a set of final states. A subset of these states where if I actually end up there when I'm finished reading the string, tell me that I accept it and I say yes. And if I end up in the non-final states, I say no. And the way to indicate final states in my notation, and I'm pretty sure the book does the same thing, is just to put a double circle around the state. So that's this one. That's a complete finite state machine. This accepts all binary strings that have an even number of zeros, and it rejects all binary strings that don't have an even number of zeros. And we can run it. 0, 1, 0, 1, 1, 1. I end up here. I look at the double circle. I say, I accept. And that string is a yes. All right, are there questions so far? Who's got it? Too easy? So far, too easy? Good. Nothing like too easy.
Depends on whether you read the book or not, I guess.
Oh, okay. Yeah.
Wouldn't it be yes, no answers, except reject?
Yes, all yes, no answers, yes. There is issues of complexity. It's not that the other questions aren't interesting. It's just that let's solve these questions first, because they're hard enough. It's hard enough just to deal with computation with yes or no. And then later on, we can put in the issue of actually outputting something, because we do that later on at the Turing Machine level. In fact, you might remember in the computer architecture course, they talked about the versions of finite state machines that actually have output. Mealy machines and Moore machines. Does that ring a bell? OK, so there are versions of this that have output. And sometimes in a course like this, they get thrown into the exercises as, hey, somebody uses this for some neat application. But you've seen that application already. And for the most part, we don't need to discuss it as far as the material in this class goes. We're going to stay away from output on finite state machines. They just say yes or no. All right, so we're going to do a few more examples of this. And an even number of ones. It's another thing a finite state machine can do. All right. So the last one that I did is the last one that I'm going to do for you. So now you guys do it, and I help out, and I correct you when you're wrong. And that way we'll discover this together. How do you do all binary strings that have an even number of zeros and an even number of ones? What's the plan? Don't say, OK, write this circle and make an arrow. Tell me how you want to represent the states. How many states should we have? What are the issues? Who has an idea? Yeah.
You could have 4 states, even zeros, even ones, even zeros, odd ones, odd zeros, odd ones, odd zeros.
So you want to do all the possibilities of number of zeros and ones, whether they be even or odd. And you'll all learned in discrete math if you have 2 bits and you want all the different possibilities of 0, 0, 0, 1, 1, 0, 0, 1, 1. You've got 4 possibilities. You think that's a good idea? Looks good to me. All right. So I got 4 states. I can name that tune in 3 notes. Maybe not 3. Here's a yeah, that's a finite state machine too. Yeah. Here's the initial state. What should this one be? Even zeros, right? So how about if I represent these states by 2 letters, E and O, EE for this one, even. So I don't have to write even number of zeros, even number of ones. This is EE, and this will be EO, and this will be OE, and this will be OO. All right, so let's go through and figure it out. What happens when I get a 0 here? I got to tell you which one is which. The first one's zeros, the second one's ones. So if I get a 0 here, I toggle this one. And if I get another 0, from here, I toggle it back. I'll fill in those 2 first. If I get a 1 here, I toggle this one. And if I get another 1, I toggle it back. Doug, want to fill in the rest? What happens here?
If you get, let's see, if you get a 0, you toggle down.
Okay.
And another 0, you toggle back.
Okay.
If you get a 1, toggle.
This way? Back this way. Is that it? Do we have zeros and ones coming out of every state? And it's right, so where should the final state be? This one. All right. Notice there is not always a single final state. What if I gave you this problem? I want something with an even number of zeros and an even number of ones, or an odd number of zeros and an even number of ones. Then it would be both of these being in the final state. Now, let's say I did do that. Let's say I changed it. So now this was the machine. Is this the smallest machine that would do this? What is this equivalent to, this set of things with an even number of zeros and an even number of ones, or an odd number of zeros and an even number of ones?
Look very much like the machine we looked at before.
Very much like it, not quite exactly, because this is an even number of ones. So in some sense, this is not the smallest finite state machine. Definitely not. In fact, we could do this with 2 states. These 2 are essentially equivalent, and these 2 are essentially equivalent for all intents and purposes. That's a very important thing to realize. When you realize this for the first time, you say, oh, gee, I wonder if given a particular set of strings, there's always some minimum finite state machine that I can get. You know, there's clearly more than one. So maybe there's like one canonical minimum one, and all of those look the same. And the answer is that there is. And that's a very, very nice thing to have about a machine, because there is no canonical minimum program to solve any of the programs you've done this year. Everybody comes up with a different one. There isn't anything special you can say about the best one or the smallest one. But for finite state machines, you can. And there's a very, very rigorous algorithm that does that minimization. And it's a dynamic programming algorithm. So everything all comes full circle. And we'll talk about that algorithm later. But it's important to know that there is a minimum finite state machine for every set that you can accept. OK, let's go on to another one. Divisible by 4. How do you know how do you do it? How do you check if a binary number is divisible by 4? Well, let me pick the bad way. I always like to do the wrong. So here's a bad way. I'll take the binary number. I know how to convert it to base 10 because I don't really understand binary numbers, but I remember the algorithm. So I go ahead and add it all up. I convert it into base 10, and then I look at it in base 10, and I know how to do division. So I do 4 into base 10, and I do division, and I know if there's a remainder or not. And if there's no remainder, then I say yes. That's perfectly okay. I mean, it's a computation, and it's deterministic. I'm never going to infinite loop in that computation. But it's kind of like tying your hands behind you and then trying to tie your shoes. It's just a hard way to do it. It's a little easier to look at a binary number and decide if it's divisible by 4 than first changing it to a base where division by 4 is not obvious and then doing the division. Division by 4 is kind of obvious. Any division by a power of 2 in binary is obvious. If I gave you a base 10 number and I said, is it divisible by 100? What would you do? You'd look at the end and you'd see if there's 2 zeros. That's the same thing here. That's 10 squared. This is 2 squared. If you want to know if a binary number is divisible by 4, you just look at the last 2 symbols. So this is just the same as binary strings that end in 0, 0. All those things are divisible by 4. So let's do that. Let's write a machine that figures out whether a binary string ends in 0, 0. Beginning in 0, 0 would be easier, right? Right? I mean, let's do that one at least. Let's make sure we can do it. Here's beginning in 0, 0. I haven't seen anything. I've seen a 0. I've seen another 0. Now I don't care what I get. And what if I get a 1? Go somewhere else. What if I get a 1? I go somewhere else, and I call this the dead state. I never accept from there. And these are all the strings that start with 2 zeros. Everyone agree? It's not what I want. I want strings that end in 2 zeros, but at least let's do something similar to what we want that's easy, and maybe it'll give us a hint for what we want to do. By the way, what's the meaning of these states? This state is I haven't seen any symbol yet. This is I saw a 0. This is I saw 2 zeros. I mean, kind of obvious meaning. How do you decide if you want to end in 2 zeros? This is harder.
You could do your 2 zeros along the top like you started, and then the end. When you, instead of just looping back, if you get a 0, you stay there. If you get a 1, you loop back to the beginning. So this third circle, if you get a 1, you loop back and start over because you don't have any zeros then.
Okay, Doug has a good idea. Let's look at it. He says, let's start with the same 2 zeros in the sense that these are the last 2 symbols we've seen. This means that my last symbol is a 0. I'll write that in here. Last 2 symbols are 0. And this is last symbol, second to last symbol is a 0. Right? That's what these things mean. The second to last symbol is a 0. The last 2 symbols are a 0. If that's the case, we'd want to accept. Well, now we've got some semantic meaning on these states. We just have to fill in the other arrows. And that's what you were doing in your head. But now I think we can do it now that we have some meaning to these states. If we haven't seen any symbols yet in this spot and we get a 1, then what? Then we stay there. Then we still haven't seen any zeros yet. What about here if we get a 1? We haven't seen any zeros yet. The last symbol, the second to last symbol is no longer a 0. Right? So we go back here. What about over here? Back to the beginning. Do we finish this? So we have zeros and 1s on every state. So let's test this. Does it really work, or is it mistaken, or is there a problem?
If you start with a 0 or an empty string,
Say it again, Seth?
if you just have like an empty number or just 0, it's not going to be the right answer.
And 0 is divisible by 4.
Right.
Right. So if I have, so the empty string I'm supposed to accept, right? And any string of zeros I'm supposed to accept, even a single 0. So can I just make that a final state? No, right?
If we make our starting point be the final state, then it should work, because if we get a 0.
So let's take away the starting state, which we maybe were too rash in how we started. Because after all, this is the place we started when we wanted the thing to start with 2 zeros. Maybe we can put the starting state here. That's an idea. Let me stop for a second before we check this. if you're thinking, oh gee, how will I know to design harder ones than this? Then let me give you the answer straight up from the beginning. This is a design process, and there is no algorithm for making finite state machines for particular sets. And every one is a creative process, and some are harder than others, and some you can stare at all day long and not know how to do, and some you'll get right away. So there is practice involved, and there's tools that you develop. And that's why we're doing these examples. Let's check this now. So Seth had a good objection. He said we're not accepting single zeros and we're not accepting empty strings. Well, now we kind of are, right? We certainly accept the empty string. Do we accept a single zero?
Yeah, because we're missing an arrow.
Right, well, that's another thing. We never finished this machine, right? I said it's finished every zeros and ones out of every arrow. I lied, right? There's no zero out of here. Zero should go back to itself. If the last two symbols were 0 and you get another 0, then the last two symbols are still 0. So now we've got that nice accepting single zeros. We accept the empty string, and we accept anything that ends in 2 zeros. So there was a process here and a discovery, and it took a little more time. Let me give you a faster way that we might have done this if you had known something in advance. Let's say you knew that if you could accept a particular language, that you knew a way to accept its reverse. Let's say any time you knew a language and how to do it and how to make a machine for it, and I told you, do it for the reverse of that language. What does the reverse of the language mean? It means every string in the language just gets reversed. So what's the reverse of things that are divisible by 4?
2 zeros.
Things that start with 2 zeros. What if you always knew, given a machine for one set, how to get the machine for the reverse? What if there was a process, an easy process? Then you'd think about this, you'd say, gee, ending with 2 zeros, that's like the one we did in class. And it wasn't quite so easy. But I know a really easy way to do things that start with 2 zeros. I'll just do that, and then I'll figure out the way to reverse it. All right, so there is a way to do that. And there's a way to do lots and lots of these, what are called closure operations. There's a way to do reverse. There's a way to do many, many things like it. There's a way to do complement. And these closure ideas are a key thing that people think about when they talk about models of computation. Not just because it's interesting mathematically, but because it gives you a whole repertoire of tools to decide whether or not a set can be accepted by a finite state machine and how to do it. Knowing the reverse here would have helped us. We did it anyway because we're smart, but you never know when that's going to fail you. Okay. What if I asked you for all the binary numbers that aren't divisible by 4? Do we start from scratch? Yeah, what if I just take this final state, good idea, Sham, make it a non-final state, and take these two non-final states and make them final states. I just toggle all the final and non-final states. Whatever used to not be accepted, I now accept, and whatever used to be accepted, I now don't accept. And that actually is a good enough proof that finite state machines are closed under complement. That means if you can do one kind of set, you can do its complement. Just toggle the final and non-final states. Right? So that's the first closure proof we've actually done. It's pretty straightforward. There's a lot of other ones that we'll get to later. All right, any more questions about this? 1, 1, 0, 1, 1, 0. I mentioned that one of the big applications of finite state machines are building string searching tools in editors. So, well, here it is. Here is a string we want to search for. Build me the finite state machine that accepts any string that contains this. And then you could actually implement that as a program. And there's actually not obvious ways to do it. There's a lot of good and bad ways to do it. There's a whole area in algorithms called string matching. And it's based on finite state machines. And it's clever ways of implementing finite state machines in order to search for strings. And the first one of those was due to Knuth, Morris, and Pratt. And I think we even did a recitation on it back in a few months ago. But now let's just write a finite state machine straight. Who's got an idea? Where do we begin here? Chris, you have a
series of states representing progress along that line as we're matching.
Okay, we're going to have a series of states that represent how much of this string we've seen. And if we actually see the whole string, then at the end we'll put a double circle. So let's do that. We start here. I've seen a 1, that's good. I've seen another 1, that's good. I've seen a 0, very fine. A 1, a 0. And I accept here. And I'll put little semantic notes in my states. Here I've seen nothing. The book uses an epsilon or an e to represent the empty string. Some books use a lambda to represent the empty string. Different books use different things. And I will try to use an e, but sometimes I may forget and use a lambda. It just means no string at all, just the empty, the null, the 0 ASCII value. This says I've seen a 1. This says I've seen 2 1s. I've seen 1 1 0. I've seen 1 1 0 1, 1 1 0 1 1. And here I've seen everything. All right, so now we just got to fill in the rest. And how easy or hard is this? Well, let's try and see. Say I'm here and I get a 0. Then how much of this string have I seen? None of it. Say I'm here and I get a 0. Then I've seen a 1 0. That means I've seen none of the string. Back to here. Here I've seen 1 1. And if I see a 0, I go here. What if I get another 1? Because I've still seen 2 1s. Right? You can all see that this is a little bit, you got to use your head when you're doing this. There's actually a complete mechanical process to build this machine. And that's what the Knuth-Morris-Pratt algorithm is all about. It's how to build up an array that represents this machine in linear time without having to do too much thinking. We're kind of doing it by thinking. Well, we do everything by thinking. Yes. Maybe not everything. Now what? A 0 there. 1 1 0, then we get another 0. We haven't seen any of the string then. Back to here. 1 1 0 1, if we get a 0. I think we're back to the start again. Most of the... No?
We get to go to scene 1 0.
No, I don't think so. If we get a 0 here, I don't think we've seen any of the string. Yeah.
It's the next one.
Now what about here? 1 1 0 1 1 1. Then how much of the string have we seen? 1 1 0 1 1 1. We've seen 2 1s. Okay? This is tricky. 1 1 0 1 1 1. How much of this pattern can we pull out of here from the right end? That's as much as we can. If we go back one more symbol, we have 1 1 1, and that doesn't match. So what you're really asking is, how much of this pattern can overlap with the right side? And you can imagine there's probably some mechanical process to do it, and there is, and it's clever. So this goes back to here on a 1. And finally here on a 0 or a 1. We've already seen the whole string. It doesn't matter what happens. OK. And of course, if I wanted all the strings that don't contain this as a substring, I just turn that into a non-final state and turn all these into final states. The reason I'm mentioning that is because if I started with that example, it might have taken us longer to discover this idea. The way to do things that don't contain this string is really to do things that do contain the string and just flip all the states. It's very hard to focus on the characteristics of strings that don't contain this explicitly. And it actually ends up being 6 different kinds of things. We could actually give meanings to each of these. And if you tried to do it that way, you would have spent a lot of time. So doing it this way is a quicker and a faster way. All right. Keep this example in mind, because when we add on an extra arm to this machine, we're going to give it power. We're going to give it power that turns out not to actually help it at all, but just help us write easier machines. When we give it this power, we're going to be able to write this example like that in a flash. And we're going to need a proof that this power can always be converted back to something without the power. But there's always a way to take these fancier machines and write them without the fancy stuff. And this power that we're talking about that we'll get to before the end of the day is called non-determinism. And you heard it before in the algorithms class, but now you're going to get it by a real definition and not just by an algorithm intuition. All right.
To get that machine, is it easy to get the reverse of it? The reverse of the string?
Ooh, yeah. Well,
Or the complement?
I've got the complement for sure, but the complement's different than the reverse. The complement is all the things that are not in this set, and the reverse is take all the strings in the set and reverse them. So that they might be different things.
Or if you just took the complement of each thing in the pattern. You went 0, 0, 1, 0, 0.
Oh, you mean to reverse? Well, I guess strings that contain 0, 1, 1, 0, 1, 1 is the reverse of this.
So the arrows are reversed.
Right. Well, so you're asking yourself a good question. If I have a finite state machine, how do I get a finite state machine that accepts the reverse language? We haven't discussed it yet. I said it could be done. You know what? I'll come back and we'll try to do it. It's a good question. Let's try right now. What would you do? The arrows would have to be reversed, right? The arrows go in the opposite direction. And what about the final and initial states? We want to go backwards, so we kind of want to start where we end, and then we want to end where we start. So look what happens when you do this kind of strange transformation. We reverse all the arrows. Boom, I reversed them. Poof. I turn this into a start state, and I erase its final state, and I turn this into a final state. What do you notice about that machine? There's something really strange about it.
You've got an arrow.
Leave it start state.
Oh, you can have an arrow that goes back to itself. That's okay. And this is reversed now, right?
But it can't take all the inputs, and it can't loop back to itself on all the inputs. Otherwise, we'll get stuck there.
You have 2 zeros.
True. That's true. And there's 2 zeros. So what do I do when there's a 0? Do I stay here, or do I go that way? Right? So it was a really good idea to reverse the arrows and to switch the final and the initial states. But when I do it, I get a machine that doesn't even make any sense. And it seems to be wrong. So right, I mean, well, I guess how wrong can you be when you don't make any sense? Here's the thing. This is a good idea. The idea is very good. It's just that this really begs us to ask the question, well, what does it mean to have a choice on the same symbol? If we can make sense out of what that means, maybe this method actually really works. It turns out this method does work. We just have to explain what it means to have 2 symbols on the same thing. If we say it's meaningless, or if we say, oh, we might get stuck here, then it's going to be wrong. But if we give it correct meaning, there is a way to interpret this reverse and then convert it back to a deterministic machine, and we would actually get the reverse. So it's the right idea, it's the right idea, and it's the right idea. And it's going to introduce non-determinism in about 5 or 10 minutes. Non-determinism is exactly this. You can have more than one arrow coming out of a state with the same symbol on it. So the question is, what does that mean? How do you decide what gets accepted and what doesn't get accepted in a machine that doesn't tell you what it's doing in any state? I'm going to do this or this? Nah, nah. All right, we'll talk about that in a few minutes. I'm going to do one more of these. Well, 2 more. Here's a quick one. Everyone is followed by at least 2 zeros. Binary strings again. Everyone is followed by at least 2 zeros. I want to do this one because instead of giving the state semantic meaning right away, this one is more of a left to right. Let's imagine that we're the machine. How would we do it? This is much more of a real-time left to right processing thing. Not a recursive idea, not a semantic idea. Let's go ahead and start. Here's the start state. If I see a 0, I don't need to do anything special. But if I see a 1, then I'm in a state that remembers that I'm now in the second stage of my computation. Sometimes states don't have semantic memory, so to speak, but they remember where you're up to in the computation. I've just seen a 1. Now I need to get at least 2 zeros. Otherwise, I don't accept. So in order to continue, there have to be 2 zeros. That's my continuing step. If any point along the way I didn't get a 0, I die. 1, 1. The dead state.
Should be directly followed by these 2 zeros.
Yes, directly follow. Yes, yes, yes. Right. I know you know what I meant. Yes. Thank you, Donna. If there's 2 zeros afterwards, then what? Then we're OK. And we got to look for, where are we?
We're okay so far.
And where should we continue? Is this machine going to go on forever? You know, sometimes finite state machines go on for.
0 loops back to itself, and 1 it goes back to the beginning.
OK. So can I?
Or we can just go back to these.
Tony's right. On a 0, we'd stay here. And on a 1, we could go actually to here on a 1. And if that's the case, then these 2 states are, for all intents and purposes, identical. I'm pointing that out because that's the idea of minimizing machines. What you try to do is notice groups of states that actually do the same thing, for whom it doesn't matter where you start. They always tell you yes or no together. So actually, I made a new state here, but I just realized that it's the same as this state. So now I go back, and I just wing that arrow back to here. And that's OK. Right? What you said is fine too, Tony. It would work just as well. Just the state shorter this way. All right. OK, this example? One more example, and then we're done. This is a little bit trickier, but not too bad. Binary strings that are not divisible by 3. So now you don't have the nice just, power of 2 thing, where you can just look at the end of the symbols. Now, you really have to do division in some sense on this binary string. Now, when you do division, at least the way you learned it when you were in 3rd grade, you have to store a lot of information. I mean, you have to remember, it seems, the result as you go along, and that's proportional, to the size of the string you have, and that doesn't seem like it's constant. If I give you a longer string, it's going to take you a bigger amount of space to do the division. And that's true. Division, actual real division as a computation, does take space that grows and is not finite. That's proportional to the log of the size of the string. So we can't do real division. So how are we going to do this? Well, we don't really have to do the division here. We have to just figure out whether it's divisible or not. And in order to do that, we just have to figure out what the remainder is. And you were never taught just to figure out the remainder when you were in 3rd grade. But if you were, they could have taught it to you. And all you have to do is remember 1 or 2 or 3 numbers as you go along. So let's consider what that means. Before we write the machine, this is much harder. This you can sit at for a few hours if you don't get the idea right away. Let's do this. Here's a number. We want to know if it's divisible by 3. Let's not convert it to base 10 and do the division in our head, because that just begs the question. Instead, let's pretend we're the machine, and we get to look at this left to right. So now we're staring at the 1. Let's say that was all we got. Is it divisible by 3 or not?
No.
What is it divisible by? What's the remainder when you divide it by 3 is what I mean. 1. Right? So that's what we're going to remember. We're going to remember, if I stopped right now, what would the remainder be? If I stopped right now, the remainder would be 1. Now I'm going to continue. I put a 0 on the end of my string. Let's not calculate that this is a 2, and therefore 2 is divisible by 3. Let's calculate how the remainder changed when I put a 0 on the end of a string whose remainder divisible by 3 I already knew. Let's do it recursively. This is a recursive idea. If I knew the remainder was 1, and I stick a 0 on the end of the string, what happened to the string in size? It doubled in size. If I double a string in size, then I double its remainder with respect to 3. If it had a remainder 1, now it's got a remainder 2. So I double this. Now it's 2. How much information am I keeping track of? One piece of information, what the remainder is. How many possibilities are there for that? Either 0, 1, or 2. 3 states is enough to do this. Let's continue. When I move on to this 3rd spot, double it and add 1. So if my previous remainder was a 2, I double that. I get a remainder of 4, which is really a remainder of 1. Then I add 1, which is really a remainder of 2. All right, so it stays a remainder of 2. Then I move on to here. It's another 1. Double it and add 1 stays 2, same as before. And now, same thing, double it and add 1 stays 2. So when I'm all done, I know this has a remainder of 2 when I divide it by 3. Now we'll check it the other way. What is this number? 1, 3, 7, 15? No, geez. What is it? 1, 2, 4, 16. 23? 23. So 23 divided by 3 leaves a remainder of 2. Good. OK. Let's write a machine to do this. You all think you can do it? Let's try. We're going to have 3 states. This one is going to be a remainder of 0. This will be a remainder of 1. This will be a remainder of 2. And I start in the remainder 0 state because when I haven't seen any symbols at all, the empty string has a remainder of 0. Now let's calculate what happens to the remainder as I add strings on to the right end. If I add a 0, I double the string or the remainder. So doubling twice nothing, still nothing. If I add a 1, I double plus 1. Takes care of that state. Let's go here. If I have a 0, I double it. That moves it to here. And if I have a 1, I double it and add 1, which moves me. 2 plus 1 is 3. Back to here. From 2, if I get a 0, I double it. And if I get a 1, you all know I stay where I am. And there's beautiful symmetry in this example. And here's the final state. Not divisible by 3 is here and here. This or that. This brings up another difficulty with reversing a machine. Where would my start state be if I reverse this machine? It could be either here or here. Right? So we have to be really careful with this reverse idea. There's a couple issues that will come up. Okay, questions about this? We're done with examples. Brian, yeah.
I wonder if you mean something stronger, like it has to be either there or there, as opposed to just you could start it at one of the two places and that would be good enough.
It has to be either this one or this one, but not any other place. Right. The way to really make this reverse is to do something like this. Have a start state here. Get rid of these final states here. And say you can go to here or to here without seeing anything. See these strange transitions? These are called E transitions or E moves or lambda moves. And they also make a machine non-deterministic because you don't know what it's going to do. So there's lots of ways to make a machine non-deterministic. Double zeros or ones coming out of a state or adding what are called E moves. And we're going to find out in a little while, before the day is over, that that adding these things actually doesn't give you any more power. I could take any machine like this and convert it back to a deterministic machine and not have all these funny duplicates. And that's a nice thing to know, because it lets you use these things at will without thinking you've gone out of your universe. Okay, let's take a 2-minute brain break for a second and think about something else without these examples. We did a whole bunch of examples of things that are accepted by finite state machines. So I told you some things that aren't accepted by finite state machines, but let's try to come up with some simple things that aren't accepted by finite state machines. Can you think of anything that you'd have a hard time doing? And the reason I'm asking you this is because you're not going to be able to appreciate moving up to this level and this level if you think pretty much you could do everything with just this. Why have unbounded memory if you just need finite memory? I mean, why make up a Turing machine if this represents a computer? This doesn't. This is limited. This is a computer with half its brain cut out. All right, so what kind of strings can't we accept with a finite state machine that are easier to describe than just Java programs? And even Java programs, nobody could convince me there's no way to do it. I mean, I believe you, but it's not like you tried every finite state machine in the world.
Are we still talking uniquely yes/no answers?
Yes, just uniquely yes/no answers. So there's a famous one. Think about what you can't do in finite state machines. What you can't really do in finite state machines is count. The simplest thing that you can't do. You can't count to an arbitrary number. Here you can go up to 3. You're looking for substrings. You can go up to the length of the substring. You're looking for finite conditions. After a 0, there's 2 1s. You count a finite number of things. Think of any set of strings you can think of that requires in quotes here because we haven't proved that it's required, but that intuitively seems to need counting. Anybody come up with one? If you read it in the book, you can just tell me. That's okay too.
So the largest number of zeros after a 1 or something. Any of those would require counting.
Okay, so what do you mean the largest number of
That's
zeros?
not a yes or no question.
Yeah, I need to have like a condition.
Is something a Fibonacci number or something like that?
Okay, so the binary numbers that are Fibonacci numbers. I'm pretty sure that's not a finite state machine. It'd be hard to, because it looks like we need some kind of arithmetic calculation. That's a good example. Other example. Equal number of zeros and ones. That's another very good example. For certain, there's no finite state machine that will just count the zeros and ones and tell you if they're equal. And even simpler than that, even this. Even if all the zeros come first and the ones come at the end. So that means E and 0, 1 and 0, 0, 1, 1. This set, ... This set there's no finite state machine for. Well, how do I convince you of this except send you home, ask you to try, and when you try all night and all 30 of you don't come up with it, I'll say, well, that's 30 more people who haven't come up with it. Right? So I'll keep doing this until I die, and then sooner or later I'll teach 4,000 people, and when I hit 5,000, we've proved it. Right? We need a better proof. And there's a really wonderful proof that there are sets that are not acceptable by finite state machines, but it comes up with a very abstract kind of cool set. And we'll try to get to that. I don't know if we'll get to it today, probably in a lecture or two. It's a really neat thing because it's used over and over again at the higher levels. And that proof technique is called diagonalization. We'll go through it in very great detail. It's a really neat idea. But for finite state machines, there's an even easier method of proof that even strings as simple as this can't be done. And this proof is going to be very constructive. This proof is going to be, I'm going to have a discussion with you guys in class. I say, I challenge you to do this. You say, I'll do it. I ask you a question about what you supposedly did. You give me an answer. I ask you another question. You give me an answer. And I nail you down and convince you that you lied somewhere along the way, if there really was a way to do this. So the proofs in general in this course are very constructive. They don't at all involve too much. It looks like they do if you look at the book. But they don't involve a lot of deep, difficult mathematics. They involve a lot of logic and a lot of straightforward argument. And we'll get to those proofs later.
Call it a Turing machine, or did he call it something else when he first named it?
I can't imagine that he called it a Turing machine. I did read the paper, and I'm pretty sure he didn't, but I don't know for sure. I'm pretty sure he didn't. He was a modest guy. I remember, I remember somebody said last month about somebody naming something after themselves, but now I forgot what it was. It's slipping my memory. Slipping my mind. All right. Next step. What I want to do now is talk about the issues that have been brought up intuitively twice already. One is when you have a machine that has more than one choice, a non-deterministic machine. What does that mean? And once we determine what it means, does it give us power in describing these sets more easily? And then how can we convince ourselves that it actually doesn't give us any more power as far as what sets we can compute, but just in the sense of how easy it is for us to realize that we can compute them? So it doesn't really give us any more power. It doesn't let us compute anything we couldn't compute before, but we end up realizing that we can compute things faster than we used to realize it because we have a more powerful tool. It's the equivalent with you learn machine language as your first programming language. And you understand programming through that, and you completely can program anything. And then somebody teaches you scheme. And you go, woo, well now it's a lot easier to do recursion. And everybody goes, well, yes it is. And things are much easier. But there wasn't anything you couldn't do with machine language that you can do with scheme. It's just a lot easier to use scheme. They're equivalent in power. They're just not equivalent as far as ease of use. That's what's going to happen here. If we tack on non-determinism to a finite state machine, they're equivalent power, but one is much easier to use. So here's non-determinism used to save us a lot of time. Let's do that same example. Strings that contain 110, 110. And let's make a non-deterministic machine. Before we even say what a non-deterministic machine really is, let's make one up. And by doing this, it'll motivate what it is, and then I'll explain it. So here's a fast machine to accept 110, 110. Somewhere in this string, if we're going to accept it, there's an occurrence of 110, 110. I don't know where that is. So I will read a whole bunch of symbols, zeros and ones, until I get up to the beginning of that string. And when I do, I will read that string. 1, 1, 0, 1, 1, 0. And then I will accept. Well, that's it. So you're thinking, well, that's cheating. Right? Well, it's cheating. So we have to decide what this means, give it a rigorous definition as to what this strange machine really accepts. I'll convince you after we give a rigorous definition that this machine really does accept exactly strings containing 110, 110, and then convince you that we can turn these machines into regular deterministic machines, and when we're all done, it would look like that other complicated one I had on the board that has just a single 0, 1 coming out of every circle. So what's that process for converting it? And more importantly, what does this mean? How do we interpret whether we accept or reject a string coming into this machine? All right, well, here's the definition, and it parallels what I want this machine to do. The definition is, if you can look at any string that's given to you as a candidate and figure out some choice through this machine that ends up in a final state, then you accept that string. There can be lots of choices that don't end up in a final state. I don't care. But if you can find one set of choices that end up in a final state, then we accept the string. So here's an example. Let's say the string looks like this. Let's say the string looks like this. Here's one choice. 1, 1, 1, 1, 0. 1, 1, 0. There's no 0 out of here. I'm dead. I don't accept. That was a bad choice. You can have lots of bad choices in a non-deterministic machine. It doesn't mean you reject it. Ending up in a rejection state on one choice of moves, since you have two choices coming out of here when you get a 1, doesn't mean you reject it. The only way you reject a string is if none of the choices get you to a final state. If a choice gets you to a final state, you accept it. If none of them get you to a final state, then you reject the string. So the definition of accepting a string in these strange machines is this, is if there exists some set of choices through this machine that gets you to a final state, say yes. If there is no set of choices, no matter which you choose, that ever get you to a final state, then say no. So should we or should we not accept this string?
Yes.
We should, because it has a 110, 110 in it. What set of choices will get me to the final state? 1, 1, and now I don't stay here anymore. It's time to move on because I just found the string. 1, 1, 0, 1, 1, 0. And from here, I'll chew up anything that comes about. So how can I convince you that this machine really works in general, not just on this string? Anytime there's a 110, 110 in my string, I will eat up all the symbols before it, ending up here. And then I'll choose to move over to the 110, 110, and I'll end up in the final state, and then this will eat up the rest. So I can definitely accept all the strings I'm supposed to accept by making that choice. How do you know that there aren't other strings that might get accepted by this by accident? How do you know that there aren't other strings that don't contain 110, 110 that might end up here? How can you convince me that nothing ends up here except strings that have a 110, 110 in them?
You no longer have a choice once you make it first even.
Because once I start off on this, the only way to make it all the way to here is by seeing a 110, 110. There's no way, no matter what choice you make at this point, that you could sneak over to this final state without going through a 110, 110. So this machine, as defined by what non-deterministic machines mean, accepts the same set of binary strings that contain the substring 110, 110. And it's also a lot easier to write. And in fact, it gives you a template for any string searching. Right? Just put a 0, 1 here, a 0, 1 here, and stick the string you're searching for in between. And the non-deterministic choice is over here. Are there questions about this? Non-determinism is going to take a little time to get used to. There are a lot of things that work with determinism that don't quite become analogous in non-determinism. So you have to be careful. Here's one. What if I toggled all the states here? I changed a final state to a non-final state and a non-final states to final states. In deterministic machines, what happened when we did that? We got the complement of the set. We got all the things that didn't contain 110, 110. What if I do it here? What does this machine accept if I toggle the final and non-final states, according to the definition of non-deterministic machines.
Always accept everything.
It'll accept everything. As long as this is a final state, I have a choice to stay here on everything. I can get everything. That's not the complement of this. So what you should realize is that complementing non-deterministic machines doesn't work by toggling the states. The only way to get the complement of a non-deterministic machine is to convert it first to a deterministic machine and then complement it. And the reason is that the definition here is not symmetric. You accept something if there exists a way to a final state, but you don't reject it if there exists a way to a non-final state. You reject it if all the ways don't exist to a final state. So it's that asymmetry in a non-deterministic definition that makes this complement thing not work. There's a lot of subtleties there, and they correspond to non-determinism at these other layers. So if you get used to non-determinism at this layer, and we'll be spending some time on it, you'll have a much easier time with it as we move higher up the ladder. Okay, questions?
The
Yeah.
finite state one seems to work, but this one, needs another control thing, right, in order to work.
No, because we don't know what it's going to do.
You have to know when to go down the tempo.
Well, yes and no. We don't, a deterministic machine, we actually think of it in real time. We think of it as chugging along. State, next state, next state, next state. Symbols are done, I'm done. There is none of that with a non-deterministic machine. It exists kind of in this abstract world. And it doesn't really do any computation on this string per se. It does lots of computations. You'll see a picture in the book that looks like this, and it's a nice picture. Here's a deterministic machine on this string. It starts here, and it moves from state to state to state. How many symbols here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a deterministic machine. You look here, and if it's a final state, you say yes. If it's not, you say no. Here's the equivalent computation for this machine. On the first symbol, it has two choices. It can either stay here or go there. On the next symbol, it has two choices. On the third symbol, two choices. A computation for a non-deterministic machine looks like a tree. A tree represents kind of all the parallel computations that can be going on at the same time. When do you accept the string? If there's a path from the start somewhere down that ends in a final state. If any of them end in a final state. When do you not accept a string? When all the paths from the root on the bottom have no final states.
So the idea is that it can try them all at the same time and pick the one that works?
Exactly. The idea, the power is that it tries all its possibilities simultaneously and picks the one that works, which should remind you of what we did in algorithms. That's right. That's the connection between what we did there and what we did here. Non-determinism lets you do ors in parallel. This or this or this all get done at the same time. Does that make sense? Does that help a little?
Yep.
Okay. Something else I was going to say about this once we're here.
With this particular machine, it doesn't branch out quite that bushly.
Right, because when you get to this other spot, there's no choice. Right, right. So it's two choices on the first one, and then this choice doubles, but this one is single. That's right. That's right. Right. I mean, if you stayed here, you have two choices for the next one, but if you move there, there's only one choice. You'll also notice that in non-deterministic machines, you can leave arrows out. If you leave arrows out, there just aren't paths there. It's kind of like our dead state for the deterministic machine, but it's perfectly fine to leave arrows out of a non-deterministic machine. A deterministic machine needs an arrow on every state for every symbol. So Chris said before that this is like doing all the computations in parallel and looking for one that makes it, and that's a good way to think of it. I'm going to do that ending in 2 zeros. I'm going to make a non-deterministic machine that ends in 2 zeros, that accepts all strings that end in 2 zeros. And then we're going to convert it to a deterministic machine by a very, very mechanical process that you could write a program to do. And that will prove that any non-deterministic machine can be turned into a deterministic machine, and therefore non-determinism gives us convenience but no extra power. Okay, and that'll be the last topic today. So let's do this. Let's grab the power of a non-deterministic machine and make one that accepts all strings that end in 2 zeros. How do we do it? Similar to what we did before. You have a 1 and a 0 here that just chew up as many symbols as you want. And this is similar to trying them all at the same time. Sometimes people refer to non-determinism as guessing. Since you can try them all at the same time, we can also think of it as not trying them all, but just guessing the right one. If there is a way to do it, we like to say we're guessing the right way. We're taking the right choice. So you hear people use the word guess a lot with non-determinism. That really bugged me when I first learned it. I go, what do you mean guessing? How do you know if you get it right? And then later on you guess and you have to check if you get it right. And sometimes you check and sometimes you don't. So I'm going to try to stay away too much from that term because it bugged me and maybe it'll bug you. But it is a perfectly fine term. It just took me time to get used to it. You chew up all these zeros and ones, and at some point you guess that you're done. So you're up to the second to last symbol. Here's a 0. Here's the last symbol, 0. And then you accept. This time there's no loop on this last state. We don't want to chew up any extra symbols. We want to really end in 0, 0. Anything out of here is dead. And this is it. Any string that this accepts has to have a 0, 0 on the end of it. Otherwise, you can't get to a final state. And any string that has a 0, 0 on the end of it has a choice that will make it go here. Just eat up all the symbols until you get to the 0, 0, and then move along this path. So we accept all the strings with a 0, 0 on the end, and all strings that don't have a 0, 0 on the end, there is no way to accept them. Therefore, this machine works. You have to do both those things to describe why your machine works. That you accept all the things you're supposed to, and that you don't accept anything you're not supposed to. Because it's easy to accept things you're not supposed to with a non-deterministic machine by accident. But we're okay here. So now what we're going to do is convert this back to a regular deterministic machine in a mechanical process that will be very logical. Yeah.
What happens if you hit just 2 zeros going through the string? Then you're going to sit in that end state.
Yeah, that would be a... Oh, I see. No, because here, Neil's asking about this. You want to make sure we don't accept something like this, right? So it's true you can do 0, 1, 1, and then make the choice, guess. Now I'm at the end of the string, I go 0, 0, but there's no arrows coming out of this final state, and there's still a symbol left. So if I get a 1 out of here, I die, I crash. In other words, if you're doing a computation, well, I guess it's a new rule in some sense. If there's no arrow telling you where to go, then you don't go anywhere. Then you don't accept. I could just do this also. I could put it in like this. That would be explicitly putting in the dead state. It would be equivalent. But leaving out arrows means that they go to dead states. That's the assumption in a non-deterministic machine, and you can define it that way.
But if you're at that final state and you got another 0 in, wouldn't you still have an acceptable string, or would you just be saying that?
That's a good point. Sharon made a good point. What if you were there and you got another 0, right? And then it looks like you rejected it, right? So how would you accept something like this? Well, the point is that actually we made a bad guess. If we pick this 0 to be the second to last and we go 0, 0, and then we find ourselves with one extra string, it's true we won't accept it, but there's still a way to accept it. We just have to make our guess over here. So that's an important point. It's not symmetrical. Just because there's a lot of ways to not accept strings you should accept doesn't mean that there isn't a way to accept them. Does that make sense? So the point you brought up is really good. And it's subtle, yeah.
It would also still be valid, I think, if you just had an arrow with a 0 going back to itself on that final state, but no output for 1.
That would certainly be fine. Right. But you know what? That's like screaming determinism. You have to think too hard. In non-determinism, your gut instinct should be to leave it blank because you want to end there and you're done. But you're 100% right, and it shows good understanding of the deterministic way to look at it. You could certainly loop back there. That would be perfect, yeah. Question?
It's kind of like allowing finite state machine system crashes.
Exactly.
Say that if
Exactly.
you get an extra thing, you can't go anywhere, you crash.
That's a very good way to put it, right? Heather's got a good way to describe it. If you're actually still reading a symbol and the machine doesn't tell you what to do, that's like you got interrupted. That's like, unknown instruction. Die, and you don't accept. So the machine can crash. right, let's turn this machine into a deterministic machine in a way that you'll be able to do for all the others, any other non-deterministic machine you have. The way to do this is to first label the states. We need to have some way to refer to them. So call them whatever you want, A, B, and C. And what we're going to do here has applications all the way throughout this whole hierarchy of finite state machines. So I want to make sure everybody gets it. We're going to pretend that we are another finite state machine that's deterministic, and we are trying to make the decision as to whether this finite state machine accepts or doesn't accept. And here's what we're going to do. We're going to keep track of where this finite state machine might be. We're going to keep track of all the possible computations this might make in another finite state machine that's deterministic. Sounds a little vague. Let's be more specific. I start in state A in my new deterministic machine. If I see a 0, where could I be in this machine? I could be in A or in B. I'm going to remember that in a new state by just writing the states in there. This represents that I could be in state A or B. I'm going to make another finite state machine that keeps track specifically of what states I could possibly be in after I've read through any string at all. If I get a 1 here, where could I be? Just in A. That's easy. Now I go on to AB. I'm in A or B. I get a 0. Where might I be? A or B? I get a 0. I could be in A, I could be in B, or I could be in C.
Would you really be able to be in B?
Yeah, because I might have been in A here. And from A on a 0, I could be in B. Yeah, so I could, definitely. Well, what about a 1 on an A or B? Well, there's no place to go on a 1 from B. I crash. We'll call it a Heather crash. And then from here, you're now immortalized. And from here, 1 goes back to A. So, yes, A or dead. Yeah, I'm going to leave the dead out for a minute. Maybe I should put it in. Should I put in dead?
Wait, that would make it not deterministic.
No, it's still deterministic.
If it has 2 possible places it can go on a 1 from A or B. Either
No, this state has only 1 arrow with a 1 coming out of it.
Oh, okay.
Right?
But that doesn't account for the dead.
Yeah, to put in dead.
Oh, to put in the, you're saying,
That would be a second.
we can't just put another 1 into a dead state. Right. We'll talk about the dead state later. Let's deal just with the states we have here, because all we're trying to do is keep track of where it might be in this machine. We don't have to keep track of where it might not be in this machine. It's a little tricky. Where are we done? We did 0, we did A, we did AB. Now we're going to do ABC. If you're in ABC and you get a 0, where can you be? A, B, or C. And if you're in A, B, and C and you get a 1, back in A. Well, that's convenient. Now I have no more new states to deal with.
How can you be in C again? If you're in C and you get a 0, wouldn't you be dead?
If I was in C and I got a 0, I'd be dead. But if I was in B and I got a 0, I'd be in C. So this is the set of places that I might end up, assuming that I'm not crashing. This is a deterministic machine that is keeping track of where this machine might be after reading any number of symbols, assuming it doesn't crash. Let's run it through in an example.
Is it like there's an implicit or dead in each of those states as well? Or how does that?
No, not really. It's really just keeping track of where this machine could be, assuming this machine... See, this machine doesn't really want to crash. So...
With its free will.
Let's think of it. This, if we run through this machine, which is deterministic on a particular string, let's actually do it. Let's run it through on 0, 1, 1, 0. So here, Chris, 0, 1, 1, 0. That means I can tell you without even looking at this machine that if you ran this on this non-deterministic machine, the only places you could end up would be in A or B. How? I could do 0, 1, 1, 0. That leaves me in A. I could do 0, 1, 1, 0. That leaves me in B. I can run a machine through on this deterministic machine that you just created and tell you when I'm done where it could possibly be in this machine. I don't ever want it to be in a dead state, so I didn't keep track of when it might be in a dead state. So there's no implicit or dead state, because non-deterministic machines only accept things that end up in a final state. So I don't really care when things go to dead state, so I'm not keeping track of it. Okay? So we're not going to keep track of explicitly if it's in a dead state.
There's nothing that we could plug into our, there's no string that we could plug into our new deterministic finite state machine that could only go to a dead state.
That's right. Right. And if there were, then there would have been a dead state in here that would have carried over. So you can get dead states in here, but they have to kind of come from here to begin with. Do you understand that? It's a little tricky. Well, so let's look at this. So now that we have this thing, how do you know which strings are going to be accepted? How do we take this deterministic machine and make it accept the strings that this thing accepts? This thing accepts strings that end up in state C, right? So if I run through it and I end up here, 0, 1, 1, 0 ends up in AB. I know I should not accept it. The only place 0, 1, 1, 0 could ever end up is in either A or B. That means that it doesn't get accepted by this machine. There is no way, no matter what choice you make, you'll ever end up in state C, so you don't accept it. What about things that would end up in this state? You don't accept them. What about things that end up in this state, ABC? You would accept them because there's a chance for it to end up in C. And you're saying, well, what if it doesn't? Well, in non-deterministic machines, there only has to be a chance. If there's any way for it to end up in C, then we say, I accept. And that's what I've kept track of. Where might it have a chance to end up? That's what I care about. So any one of these states that contains any final state from your non-deterministic machine becomes a final state in your deterministic machine. We're going to double circle this one, that means. And this is a deterministic machine that does the ending in 2 zeros. Is it the same as the one we did earlier in class? A little different? I think we did it with an extra state, right? Is it exactly the same or not the same? I think it's exactly the same. Is it the same, Todd?
Yeah. Yeah, with the
Yeah, it's exactly the same.
difference of where the start symbol is.
Right.
Oh, yeah, right.
Wait, what's
So this is end in 2 zeros before we did divisible by 4.
Right, right. They're a little different. That's correct. Right, right. Seth pointed out the difference. Divisible by 4 includes empty strings and single zeros, and ending in 2 zeros just means you have to end in 2 zeros. So this machine actually does not accept things divisible by 4, right? It only accepts things that end in 2 zeros. We'd have to change the final state here. Right, good point. Good point there. So there is a subtle difference between the two, but for the most part, they're identical. This process can always be done. Say, we're going to quit in 2 minutes now. Last question of the day. When we did this process, the number of states stayed the same. Didn't grow at all. There was no trade-off. Just did a little work. We turned non-determinism to determinism. But there is a trade-off that could happen here. It could be worse. How much worse can it be? How much bigger can this machine be than this machine? What kind of payoff is there? The payoff is going to be in the number of states. Here, we didn't get any more states once we got these. But what is represented in these states? How many possible states could have shown up in the worst case? Combinations, or you're thinking the right English word, but you're not saying the right math word. If the states, subsets. If the states are A, B, and C, then a state in this machine is any subset of A, B, C. Right? So we only have 3 subsets that show up. A single A, an A and a B, and an A, B, and a C. We might have gotten more by going through these arrows forward on zeros and ones. What's the amount of subsets we could have gotten with 3 things to start with? How many subsets are there in an n-element subset? That's why we did a whole month of discrete math way back there. Who remembers? 2 to the n, right. So there's 8 possible subsets. None of them, all of them, every 0, 1 toggle possibility. There's 8. This machine could have been 8 states in the worst case. In general, the payoff from going from non-determinism to determinism, or the trade-off, or what you have to pay in order to get that, is an exponential growth in states. Now, we don't really care because it's still finite. But when we talk about things in this layer, in the Turing machine layer, that exponential trade-off in states turns into an exponential growth in time. And it's the same idea. And that's why when we trade in non-deterministic algorithms for deterministic algorithms, we end up getting exponential time deterministic algorithms when we had polynomial time non-deterministic algorithms to start with. So you see it now in its most fundamental way in this trade-off in the number of states. Okay, so to review, we did deterministic machines. We explained the semantics of designing them. We talked about closure ideas just very briefly. We talked about things that might not be accepted by finite state machines. We talked about non-determinism and its extra power and how it's really not extra power, but just extra convenience. Okay, and we'll continue with this stuff next time, understanding finite state machines completely. They're completely understood. It's such a nice level and a layer. When we go up higher, things get a little more vague.